Good morning and welcome to this parallel session on the community workshop on climate adaptation. My name is Jaroslav Mysiak. I'm from Euro-Mediterranean Center on Climate Change, and I will be your chair for the first half of this session. So thank you for being with us. I hope you have had a nice evening and you have joined the opening plenary session on policy. From that session, you might have heard that there are great expectations for the implementation of the new EU adaptation strategy on adaptation modeling, filling the gaps. So this whole workshop is basically to summarize the recent development in the adaptation modeling, to present the result of the study commissioned by DG Klima, that will be tomorrow, and to enable the community of modelers to exchange views and understanding of the current state of the art research. This community workshop is also a test. What we consider for the future is to create a special community, user community, and annual or biannual conference co-sponsored by European Commission, DG Klima, that would repeat the same experience. So this is in the place. This is what we are looking into. This first community workshop was meant to be held in a physical environment in Brussels. Unfortunately, due to the COVID-19 lockdown and security measures, we are unable to do the physical workshop. That might be done next year. So in order to not to lose time, we decided to turn into a virtual workshop, as several other major scientific academic societies have done before. And we hope you will find this experience useful and enlightening. So I will only explain very quickly the housekeeping rules. You have 12 minutes for the presentation and then 1-2 clarifying questions from the audience. There will be a coffee break in about 1 hour. After the coffee break, we resume this work stream, and we'll finish by 12:30. And 12:30, we will move to the plenary session and do the wrapping up, listening to the different moderators and rapporteurs, what has been said in working streams, and summarizing the discussion. So a part of sticking to the time, please get your presentation ready. When it's your turn, we will try to stay on the agenda. And I would invite the first speaker, Agustín Sánchez-Arcilla from the University of Catalonia, to take the floor.
All right. Thanks for inviting me to be here. I will share my screen. Can you see my overheads?
Yes. Yes, we do.
All right. I'm going to give you a brief summary of the work we have been doing recently on numerical and hydraulic modeling for coastal adaptation. Of course, all applied to the Catalan coast. The research work has been done in the frame of H2020 projects, and we have reached an agreement with the responsible administration to convince them and to introduce our results into the additional adaptation we believe is necessary, because we were already adapting. But our point is that we need additional adaptation. Main message is the Catalan coast is about 50% active. Active means that it dynamically reacts to sea level rise, so it's a sedimentary coast, and the rest is non-active. And about 20%, so just 1/5, has the possibility to accommodate, has some space for managed realignment. For the rest, of course, everything is possible, but it's not easy to move back or to realign. And in spite of that, we are having regular storm impacts that happen every time more often. We attribute that to climate change, This is the result of the January 2020 storm called Gloria, produced damages. I will go from top to bottom on beaches, on a coastal pier very near Barcelona that we have instrumented for nearshore research, produced damages on breakwaters, and it also clogged harbor entrances with a beach about 50 to 100 meters wide. That in the period of 3 days. Of course, those conflicts and the present conditions will aggravate the future climate. By way of illustration, there you have a projection of the shoreline near Barcelona that is, of course, taking into account, not taking into account the human-built barriers, so the buildings, that is assuming that the beach reacts dynamically, and as you can see, part of the maritime districts or quarters of the city will be underwater by 2100. One of the main difficulties we found for carrying out numerical simulations, numerical projections, but also for analyzing the behavior, the response of beaches in a wave flume or basin is the lack of an updated bathymetry. We have been using Sentinel-2 data with a revisit time of, let's say, about 6 days, but it's only suitable for very shallow depths. We do not have a submerged LiDAR flying regularly, so what we are using right now for the administration is drones, floating drones, like the one that you can see on the right-hand side picture, that monitor about once every 3 months the topobathymetric conditions. The more vulnerable sector of the Catalan coast are quite clearly also the deltas. We have 3. The largest one, which is the Ebro Delta, is our top vulnerability hotspot, and it is largely disconnected from the river basin. Only about 3% of the river basin is connected directly to the delta. So that means that the solid river discharge has been reduced by 3 orders of magnitude. So that is a lot, and of course the delta is suffering the wave climate, which is essentially as it was about 100 years back, but also the mean sea level, which is rising at an accelerated rate because that delta is also suffering subsidence. So locally, the effect of climate change, in particular relative sea level rise, is increasing, although basin-wise, it's difficult to say because it will mainly depend on river regulation policy. Because the delta is so flat and is sediment starved, as you can see in the top picture, any storm or any surge has dramatic consequences. The main paradox that we have to face is that there are no coastal engineering works along the shoreline. So many people think that the delta coastline is pristine, and we are, let's say, telling them that is far from being the truth because the river is heavily regulated. So we are looking, and that is what we are analyzing with our hybrid modeling approach, numerical and physically, sustainable solutions, basically nature-based solutions, which prevent the loss of territory and the loss of functionality. Main one would be increasing the sediment supply, that is moving sediment from the reservoirs to the coast, and recycling the sediments, taking it from the ends of the 2 spits of the 2 peninsulas and moving it to the red areas where there is stronger erosion, always with the aim of keeping a functional beach fringe. The types of, I will only present 2, the types of nature-based solutions we've been analyzing let's say, using the results, as I said before, of research projects, but also according to the wishes of the responsible administration, are vegetation, in that case, seagrass meadows. It was quite well known, the behavior of dune grass, but seagrass meadows were more uncertain and also more difficult to restore. We've been analyzing them in the flume because they have a certain capacity to self-regulate, so to move towards the shore with increasing sea level, but also because they have a low carbon footprint and they are energy-wise very efficient. That is an example of the hydraulic modeling we are carrying out of that seagrass bed, and we have tried to test actual seagrass in our flume, but our flume works with fresh water because of obvious reasons. Otherwise, everything would be, let's say, rusted very soon. So we need fresh water to maintain the flume in proper conditions, and to carry out optical and acoustic measurements, we need clean water. And that means using surrogate, essentially plastic PVC seagrass. We've spent a significant amount of time analyzing the scaling laws for that seagrass bed to mimic the actual behavior of seagrass in the field. Once we had those scaling laws, we've been running a number of tests, and here I will only show you one example from hydraulic modeling, which is on the left-hand side. That is the effect of a seagrass bed. That is the green patch you see on the left-hand side of the figure. And the main effect is to displace, depending on the number of waves you impose on that beach profile, to displace the breaker bar towards the shore. That is, that makes it much easier to recover that sand afterwards, either by natural means or by artificial means. Using the wave damping results from the hydraulic flume for different sea levels, we have run a wave model, a Boussinesq model in that case, to analyze the efficiency of seagrass beds at the entrance of a harbor. That is a harbor from the Catalan coast that had problems for too high waves inside the harbor domain, and our proposal has been to reduce that using vegetation at the entrance, which has also some secondary effects, of course, but we can discuss that later on. Based on our results with seagrass beds, we have also analyzed the morphodynamic response. There on the left-hand side bottom, you see the morphodynamic evolution of a barrier beach with and without seagrass bed, and then we have applied that to assess how efficient are seagrass beds to reduce wave erosion and surge flooding for that is a beach in between Barcelona and the Ebro Delta, let's say about 100 kilometers south of Barcelona. So the percentage of wave reduction that we obtain is not too high, as you can see, it's about 15%, 14%, but it is enough to reduce in the short term the main problems that we expect to be facing a few decades from now. And that is the last case I will present, that is the northern peninsula of the Ebro Delta. It is not a very large bay. Maximum depth is about 4 meters. It's 6 kilometers long and 2 kilometers wide. And the natural solution we have been testing, first with results about mixing in our wave basing, and then with a numerical 3D circulation model, is increasing land discharges, those two yellow arrows. That's irrigation water with nutrients part of the year, but clean the rest of the time. And combining that, or let's say allowing that increased freshwater discharge with favorable wind events, wind from the northwest that favors the renovation within the bay. With that, we have shown that it is possible to reduce the peaks of temperature and concentration that is normally a very serious problem for all the aquaculture activities inside the bay during the summer period. Summer period that every time is getting longer due to global warming. In a nutshell, what we achieve is the initial local flushing time, an average for the bay is about 16 days, so 2 weeks and a half, by imposing a discharge of 7.5 cubic meters per second or 10 cubic meters per second, we reduce those 16 days to about 6, so about 1 week. So it is efficient, provided we monitor the wind conditions and we make simultaneous land discharges with those favorable wind conditions. That is the natural base solution.
1 minute and a half.
Yeah, to the administration, and they are very keen on putting that into operation regularly. It has been already tested in the field, not only with numerical models and hydraulic models, also in nature, and it's working with a limited energy consumption and carbon footprint. And the effect on temperature is very good for peak temperatures, inside the bay, not for those sheltered points in the innermost part of the bay. the peak temperature may decrease between 1.5 and 4 degrees. The average temperature only decreases by about 0.1, 0.2, depending on conditions. I'll speed up a bit. This is my last overhead. And then what we have been promoting is the use of combined numerical and hydraulic models for designing those adaptation pathways that we believe will serve to better prepare our course for the additional adaptation that we will require in the coming decades. We shall be using numerical models for projecting the behavior of those solutions, or for projecting the behavior of the course without the solutions. That should allow to assess the efficiency and also to identify before they happen the tipping points. And then what we have been advocating is the use of hydraulic models for making sure that our numerical models taken outside the present range work with the same level of reliability. In particular, for the morphodynamic damping, when the submerged profile that we have is different from the one we are facing today. With that, we are building this type of diagrams. This vertical axis would be concentration in the water, nutrient concentration or water temperature, that is time. And then with those models, we are able to announce before they happen, for instance, that first warning, depending on your RCP, depending on your scenario, you may project that happening by 2030 or by 2100. If you're optimistic, it will happen by 2100. If you're pessimistic, by 2030. And then the final point of no return, that would be the tipping point. So that's basically all I wanted to share with you this morning.
Thank you very much, Agustín, for this exciting and very interesting presentation. I don't see any question from the audience, so I would have one generated. I would like to draw attention of all speakers to. Where do you see the major knowledge gaps in your adaptation modeling approach? Where do you see the gaps and where do you see the potential for making huge improvements?
Yes, the main gap that I see in our present knowledge is the two-way feedbacks between, say, morphodynamics and biota. So we have a certain knowledge about how vegetation damps hydrodynamics, so reduces incoming wave energy, damps the currents, and also damps the erosion of the seabed. But that vegetation can only survive for a certain interval of accretion erosion. Once we exceed or we go outside that interval, the plants will not survive. And there is very limited information on those intervals. So what I think we need is scientific knowledge about that, those interactions between morphodynamics and biota, and also deriving from that knowledge engineering criteria to facilitate the uptake of those flexible solutions. Otherwise, that will not happen quick enough because there's a lot of doubts and uncertainty. And it's very difficult to generate investment for nature-based solutions when faced by those uncertainties.
Thank you very much, Agustín. May I invite our next speaker, who is Edoardo Borgomeo from the University of Oxford, to take the floor and give us his view on the adaptation modeling. Good morning, Edoardo. The floor is yours.
Thanks for the invite. I actually had a question for Agustín, if that's okay, on linking.
No, unfortunately, we cannot take the question now. We need to move.
Okay.
Thank you.
So I will start with my presentation. I hope you can see the screen. So my name is Edoardo Borgomeo. I'm a research associate at the University of Oxford and a water resources management specialist at the World Bank. And my presentation today is on water resource system modeling for climate adaptation and really thinking about how do we secure water supplies under climate change and how can water system models help us do that. And I'd like to start with an analogy which I think is helpful to try and frame the problem, and the analogies from the scientists that were working on the Apollo mission. And they framed their problem in this way. You want a valve that doesn't leak and you try everything possible to develop one, but the real world provides you with a leaky valve. you have to determine how much leaking you can tolerate. Now, I feel that this statement from the scientists that were working on the Apollo mission really applies also to the issue of securing water supplies under climate change. And why do I say that? Because we can, in water supply systems under climate change, we cannot have a 100% reliability. We cannot be robust to all uncertainty. And therefore, we as a society, as water managers, and more broadly as society, we need to try to be explicit as possible on the level of risk that we're willing to take in our water systems. In other words, we need to identify how much water shortages we can tolerate under climate change. So if you bear this kind of mental model in mind as we go through the presentation, I hope that that's helpful in then trying to understand some of this work that I'm going to be presenting. And unfortunately, current water management practice and current engineering approaches are not really explicit about this risk tolerability to climate change, because as shown in this figure here, they typically approach the water planning problem as a least cost optimization problem, where you have one single projection of water supply, one single projection of water demand, and you try to find the least cost way of closing that gap, which is what we show in this picture taken from the Water Resources Plan for London, published more than 6 years ago. These current approaches are based on hydrological frequency analysis of historical data, and they typically result also in capital-intensive infrastructure. This is the traditional approach to thinking about water supply planning, and it is now being revised. There are now methods that are coming forth that propose a new range of principles that should guide water resources planning under climate change, and therefore our modeling practices as well. And those principles obviously build on the past, but they try to then really explore 4 dimensions, which I list here. The first one is the issue of robustness. Rather than identifying a least cost way of being optimal or closing the least cost way of closing a supply demand gap under a single scenario, we try to identify an investment strategy and therefore build a model that's capable of identifying investment strategies that work well across a very wide range of scenarios. The second aspect is the issue of flexibility and adaptivity. In other words, identifying solutions that allow us to respond to new observations and conditions. And then the third and fourth point are a focus. These decision principles suggest that we should focus on trade-offs and proportionality in our decisions. And then finally, the issue of distributional impacts, including the environment. And in this presentation, I'm really gonna show some results with respect to point 1 and 3, but the key message here is that the water sector community, when thinking about climate change adaptation, is really thinking about these 4 issues and when it develops models. So now, to operationalize this principle, we have our, if you like, standard decision problem, where we have these 4 steps: identifying policy structure and metrics, characterizing uncertainty, simulating and optimizing the system, and then finding the solution. So we'll go through each of these steps sequentially, looking at an example from London, where I'm most familiar with. We think of London as a very dry place. Actually, the south of England faces significant risk of water shortages, and water companies there have a statutory requirement to think about climate change and to think about ways of adapting to climate change. So you can see that there is a regulatory environment which is conducive to testing and implementing some of these modeling innovations in the water supply planning practice. So we go on, and in the first step of this framework, we have the typical identification of policies, of investments that we're thinking about implementing in our area, in this case, London. And this is very similar to any type of planning problem. The innovation here that modelers are introducing is really a concentration more on decision metrics, so decision objectives, which go beyond the least cost optimization type of problem and try to pursue flexibility, robustness objectives. And so you can see that this rapidly becomes a many objective optimization problem rather than a single least cost optimization problem. So this is the first step. And then in the second step, which is really, I believe, where some of the key innovations in the water modeling practice are evolving, is the step around uncertainty characterization. Obviously, we're dealing with a water supply system, so we're interested in characterizing uncertainty as it relates to water availability, so climate, hydrology aspects. On the left panel here, we show one way of characterizing this uncertainty, which is through climate models. As we know, those are, they have large uncertainties on their own, but nonetheless, they provide useful information, especially on the issue of non-stationarity. So rainfall and temperature as they change throughout the century, and as they change in a way in which their mean becomes time variant, which you can see especially in the time series in the bottom, which shows potential evapotranspiration, and also in these probability density functions. As you see, for each decade in the future, they shift. So this is quite important as we try to understand how water availability shifts into the future. And then a second area of innovation is around synthetic hydrology, which has been around for a while. But what researchers are increasingly doing, which is shown here, is trying to play with time series, try to modify some of their characteristics so that we're better able to then model the impact of some extreme events. In this case, drought. This is shown on the right panel here. You see drought duration and deficit for a combination, multiple combinations of events. The red dots are the historical combinations, and the blue dots are combinations generated using synthetic hydrology methods, which I explain now in the next slide. The idea is that you have your historical time series of river flows, and that you define a certain threshold for your extreme event, which is shown with the black dotted line here. And what synthetic hydrology tries to do here in light of climate change is try to modify some of the statistical properties of the time series, especially the temporal dependence between the different time steps. We try to modify that temporal dependence to generate a drought which is much longer and more severe than the one that we've seen in the historical record. And we do that as a way of characterizing potential uncertainty to then put into our model. And so you see here that then by modify the temporal dependence, we're able to generate this new red time series, which has a drought which is much longer than the one that we had observed in the historical record. And this is helpful for water modelers to characterize and quantify robustness. Then the third step is the water system simulation and optimization, the policy, structure and objectives, the inputs as it in relation especially to water availability go into this system model, which is then run multiple thousands of times to generate results, which are then
3 minutes.
Fourth step, yes, thank you. So here we have our typical risk reduction, risk cost trade-off curve, where we're essentially showing how much the planned cost increases for a given level of risk. The level of risk is on the vertical axis and the planned cost is on the horizontal axis. The difference here and the advancement that water modelers are providing is that we inform climate change by helping decision makers identify a level of risk, essentially understand how much risk reduction they're buying for a given unit cost of their investment plan. And this is a key element that water modelers are bringing to the adaptation planning table, which wasn't there before. And as you see, there is also an objective around robustness, which is this color bar on the right-hand side. And again, the issue here is trying to really answer the question, how much are we willing to pay for a given level of robustness and risk? And then I will conclude now just showing that this is being applied in London. The water company in London is, as you can see, identifying plans over 4 dimensions: cost, environmental effect, robustness, ability to cope with future changes, and also sustainability in terms of greenhouse gas emissions. So this idea of many objective optimization of investment plans is really now acquiring momentum in the water industry. And then finally, as a way forward, I think there are 4 areas where we can expand as a water resource modeling community. The first one is on data and trying to integrate sensors and data on smart water meters. You will note that in my presentation, I didn't discuss uncertainties around water demand. And I think using new data could be a key way of characterizing some of that uncertainty. The second aspect is around the economics. I think our models need to become better at modeling water reallocation, which is increasingly becoming a key area under scarcity. And also we need to better understand some of the economic impacts of shortages and investments, which are a key input to these risk-based approaches. And then finally, we need to enhance the representation of water quality and prediction of ecological responses in our models. Thank you.
Thank you very much, Edoardo, also for keeping time and for giving us these very insightful suggestions and messages. I encourage the audience to post a question on the chat, or if you would like to take the floor, I can unmute you, and if you would like to ask the question directly. In meantime, because I don't see any question, Edoardo, you have suggested a number of ways how to both the principle that should be applied to guide adaptation modeling and the principle that you jointly put in place in order to provide a better insight on the adaptation. If I may repeat the same question, where do you see the major breakouts in the coming years or decades? So where would you expect a major development in the coming years in the application field that you just presented?
Yeah, that's a good question. I think so. The first one is on, I think, this representation of ecological responses and environmental responses. I think this is key. We need to better integrate that understanding into our water system simulators. I think that's one area. And then perhaps a second area is exploration of hydroeconomic optimization models. I see Manuel connected, so I think he can better speak to these issues. But I think we need to advance a little bit more in incorporating economics in some of these models, not just in urban water planning, which is what I was showing in my presentation, but also agricultural water resources. So I would think these 2 areas as kind of areas where we need to push more as modelers. Thank you.
Thank you very much, Edoardo. May I now invite Hans Sanderson from Aarhus University to take the floor and take us to the field of cascading transitional climate risk.
Yeah, my name is Hans Sanderson. I come from Aarhus University, and I want to give this presentation and broaden the discussion a little bit about adaptation and try to integrate mitigation into this discussion as well. And basically, in my view, there's really a need in the community of adaptation to think more about how climate change impacts the private sector and how climate change impacts the business models and the working of the private sector, basically in the transition to a low carbon economy. So that's what I'm going to be talking about. This is a huge challenge that we have in front of us, and we need to accomplish this in this decade, basically. In my view, this research area has been a little bit neglected over the past decade, where we've focused really a lot, for very good reasons, on adaptation, but really thought about it in just more of a public sector avoidance of floods and other events. And my point really is that climate change represents a huge risk to our whole economy and way of organizing our society. And that's basically what I want to be presenting just in this short presentation. So some of you may know this, this figure already. On the left-hand side, you can see the different types of risks that we are facing right now in terms of climate change. We have different mitigation scenarios, and in Europe, we're really going towards the aggressive mitigation. So we want to have the RCP 2.6. And that means that we will need to halve our emissions globally by the mid of this century, and basically have the same decrease in emissions as we had the increase since the mid of the last century. So, you know, this basically shows you that this is an enormous transition of our whole society in the European Union. Of course, we will also experience some of the effects because not the whole world is probably going to be doing an aggressive mitigation, and that's not what we have seen, at least from the IPCC negotiations until now. So we'll also have businesses impacted by more physical risks. So transition to this aggressive mitigation is really a transitional risk that is impacting businesses, and that's what I want to be talking a little bit with you about today. I also just put in this risk chart from the World Economic Forum earlier this year, and as you can see, the most likely and most impactful risk that is facing our world economy now is failure to adapt to climate change, which also includes adapting business models to that. Of course, they didn't really see a pandemic coming in that analysis, but they did that a few years ago, actually. But that's just to say that there are uncertainties in these assessments as well, of course. So this is a busy graph, as you can see, but it actually contains quite a lot of important information. So now we're focusing in on the European Union and how we're actually performing in terms of our emissions. So you can see the full line is basically our emissions so far, and you can see the dotted green and yellow line, which indicates, you know, the projections that we have with existing and additional measures. And then you can see the red dotted line down to the target. And there's a discrepancy between these yellow and green lines and then the red line. So as you may or may not know, the European Union is right now negotiating a new climate law that will increase the target from 40% reduction relative to 1990 to between 50 and 55% reduction. That will mean, as you can see in the upper right-hand corner, that climate policies will need to become much more aggressive. The current policies we have now are not on track with the desired reduction in emissions, reduction of emissions. So this is something that will be accelerating in this decade, basically. And in the lower left-hand corner of the slide, you can see, you know, what kind of additional investments are needed to achieve this ambitious goal. And you can see the 1.5 degree target that we're looking for actually requires between 175 billion up to approximately 300 billion euros additional investments each year to reach the needs that we have with the previous goal. So this is going to become much more aggressive and much more costly, or we will need to raise a lot more investments to actually meet this. Of course, this is all basically trying to align the European Union with the Paris Agreement so that we can stay below 2 degrees and hopefully avoid the most catastrophic events of climate change. So how are we basically going to do this? There's not you know, a switch you can flick or anything. You need to talk with the whole business community. And that's what's being done in the European Union right now. So there's a sustainable finance taxonomy that will be ready by the end of this year. That will go out to investors so that they can basically see and rank different companies and de-invest in carbon-heavy companies. This is really important that the investors have reliable, transparent, and harmonized information, and that is what will be provided by the end of this year, according to Frans Timmermans earlier this month. If we look at companies, that's the green chart, and there's an interview guide here that's been done with around 240 different companies 5 years ago. And they all say that they are receiving increased pressure from investors to report on climate-related risks and how they deal with them, basically. So that's the large green bars. And in the lower right-hand corner, you can see basically the same question, but now it's 140 different investment organizations and what they're basically looking at as being important in relation to climate change. So there's attention to this, and markets are shifting towards decarbonizing portfolios, and this is exactly what we want. We want to be shutting down a lot of carbon-heavy companies in this coming decade. So the real question then is, how do you actually assess this? And the whole credo from the TCFD group, which is an international group that has really informed the European policymaking in this area, is that if you can't measure it, you can't manage it. So the question really is, how do you then measure climate risks and transitional risks? And that's basically step number 2 in the framework that they have designed here. And as you can see in the lower left-hand corner, the transitional risks are all related to market and technology shifts, reputational shifts, policy and legal shifts. So this, as I showed before, you can really anticipate. One way of dealing with this, of course, is to be compliant with the science-based targets, an initiative by CDP, World Resource Institute, and WWF. And more companies are signing up to this, but there's still just a fraction of companies that are actually in this area. One way of assessing your emissions that is used by most companies is to use the greenhouse gas protocol by the World Resource Institute, going through scope 1, 2, and 3, where you have your direct, indirect, and value chain related emissions. And as you can see in the upper right-hand corner, for most companies, the majority of the emissions are located in the value chain and not in the direct and indirect emissions. So, the real challenge is to understand how to assess your emissions from your value chain.
Hans, 2 minutes and a half.
And there are different ways of doing that. The greenhouse gas protocol is straightforward and easy. In the left-hand corner, you can see that ESO has also made a more comprehensive approach. This is not mandatory right now, but it may become mandatory when these policies are moving forward, but that will require a lot more work by the individual companies. And then focusing in on the value chain related emissions in scope 3, you really need to do a life cycle analysis to understand where you can harvest cost-effective emission reductions. So in terms of conclusions and knowledge gaps that we have in this area, as you can see in the upper right-hand corner, we are really looking into a significant reduction in our emissions in the European Union. This will, absolutely change business models. It will be somewhat akin to, the collapse of the Soviet Union and East Bloc, basically moving from a planned economy to a market-based economy. In this case, we'll be moving from a carbon-based economy to a low carbon-based economy. It's going to shift a lot of things. It's not just going to be the oil companies that will be impacted. It's going to be the whole business community. There's obviously a huge need for global responsibility and taking care of your scope 3 emissions. We don't really know how to assess those right now in a transparent and good way. So there's a need to develop those methods in a pragmatic and transparent way, so that this information can go out and really direct investments correctly, so that we will actually have the financial muscles that are needed to implement the Green Deal, which otherwise simply will not happen, because we cannot raise taxes to accommodate the Green Deal. Finances has to be found in private sector in this way. So that's what's taking place as well. And with that, I want to take any questions and appreciate for your time.
Thank you very much, Hans. We have 2 questions, and I start with the one from Francesca. She basically says this is very interesting, But to shift it towards green investment, then what we need to ensure that there is a profitability on the investments.
Yes.
Where do you see the challenges in making some investment attractive to the investors?
Yeah, so what is happening now is that with the taxonomy that the European Commission is developing, it will become clear which companies that are, you know, gonna be left with stranded assets in terms of valuable products to them that will depreciate in value. And this is the information that needs to be communicated clearly to the investors. They are asking for that information right now, and this taxonomy will provide that information. So the main thing really is that as an investor, you should avoid having stranded assets, things that you know basically just lose money off, because the services and products will become obsolete in this new economy.
Excellent, thank you, Hans. And the second question is from Sergio Castellari, and he asked, you know, now given that we are investing a lot of money in the EU recovery, so how to ensure that investment are targeted on the private business as well? So what do you see as an opportunity to fuel this investment to the private sector?
Yeah, so basically, thanks for the question, Sergio. The COVID-19 recovery plan is basically the largest loaning experience by the European Union in its history. And we have the Green Deal and transition going on at the same time. So Franz Timmermans at the Bruegel annual meeting last week clarified this issue also, and said that there will be strings attached to the loans and money that will be provided to companies in relation to their climate performance. So this is something that will be coming. So as a company, if you need investments or if you need any governmental support and you cannot provide information about how you are reducing your emissions, you will be in a bad spot really, really soon. And by the end of this decade, you will most likely be out of business. That is the whole purpose, because if you see on the right-hand side, upper right corner, it is an aggressive mitigation that is needed. And that's why I think it's really important that we expand our discussion about adaptation to include mitigation and also include how we protect European industries in this enormous transition that is taking place.
Thank you very much, Hans. And this makes a perfect transition to our next speaker, who is Francesca Larosa from the Euro-Mediterranean Center on Climate Change. And she will talk about the business case for climate services, climate knowledge services. Francesca, please take the floor.
Thank you. I'm trying to understand where is my presentation. So, okay. I hope that you can see my screen.
Coming.
Okay.
Yes, we can see it now.
Okay, thank you for this opportunity. Today I'm presenting something that is slightly different from modeling itself. My name is Francesca Larosa. I work at CMCC, but I'm also a PhD candidate in climate change sciences in Foscari. I'm an economist by training, so I'll try to make the link between what is the physical science behind the climate services and how we can make the business case for them in order to support decision making. So the context of these findings is the CLARA project, which is a close to ending Horizon 2020 project, whose main objective was to develop a set of leading edge climate services for precisely 14 operating in 6 different sectors. These services are using near-term forecast and sectoral information system coming from the C3S, the Copernicus Climate Change System. And the aim of the project was not just to develop these tools, but also to understand their economic value and to sustain their marketability. So my task was precisely to look at the business model and the marketability aspects of these services. As I said, they operate in 6 sectors, so whatever I'm saying is actually valid for every sector of operation, but is very peculiar depending on the characteristics that you are looking precisely in terms of user, for example, engagements. So for those who are not super familiar with the concept of climate services, they are products and tools that transform raw climate data into bespoke knowledge, so user-tailored climate knowledge. So they are entering into the workflow of a given user, and they are telling basically how to take into account future risks and opportunity derived from climate in order to take advantage of all the workflow that the user is putting in motion. Climate services are KIPs in the sense that they are knowledge-intensive business services. They use information as key input and output. That's why they are named in this way. KIPs are highly human capital intensive. They are intangible, so they are difficult to be standardized, which is precisely what's happening in the climate services realm. And they're strongly dependent on their network in the sense that they're dependent on the stakeholders involved in the process, in the creation process, but also in the user feedback. Climate services are linking economic, non-economic, tangible and intangible present and future dimensions. And this is the reason why they embed in one single aspect a new form of service innovation, touching upon the user's experience. So again, users are very much fundamental in this process, and we're gonna find out through business models why. The approach that I've been developing within CLARA together with the colleagues is not to look at how to look at what is the climate services doing to support adaptation and increasing in resilience. Is how the climate services is actually working on a scientific base, but is instead how the climate services is going to be competitive and for whom. So using the business model lens, we're using the science-based embedded in the climate services to understand how value is generated and delivered for the specific user. So we're leveraging, analyzing the competitive advantages derived from the climate services, but we're also fostering the uptake using the most adequate channel per different service. We're supporting innovation through the links between technology, science, and information. Bear in mind that, as I said, climate services are science-based, information field, and technology allowed. So basically, it's technology with new form of data that is creating the opportunity to generate value. We're also inducing policy changes because by showing and proving that climate services are useful and are usable, then policy changes are possible in the adaptation realm. And finally, we trigger positive feedback loop to maximize the diffusion of these tools. As I said, we're using the business model lens. So in the literature, we know that business models are blurry, defined as the representation of a firm's underlying core logic and strategic choice to create and capture value that is holding within a given value network. We soon understood during the project, but also interacting with stakeholders, that business models are market devices, so they're basically allowing the market to happen. They're productivity enhancement factors. Imagine, for example, that you have an appropriate way of creating and deliver value. This means that you're really enhancing your productivity. It doesn't matter what is the basic science underneath the climate service. And they're also competition triggers. Suppose that we have two very similar climate services operating, for example, in water resources, then the way they're generating and delivering the value is the actual factor triggering competition, is the productivity enhancement, is the one that is actually allowing a given climate services to succeed in the same market. For climate services, though, we created an original business model definition because, as we said, they are not just firms operating in this market, there are also organizations, but they're very much embedded in the co-creation process. So we claim the business model for climate services entail the evolving logic, because it's not static, it's changing over time, of an organization, because it's not just public, but not just private, it can be mixed, but it can be both, to co-create value with its users. So users are essential in this process. So to promote innovation and support decision-making. This is a very important point. We're not just supporting decision-making through climate services, but we're also inducing a cascade positive effect. So if you're, for example, using climate services in order to support your decision-making, you may have a change in the way you store and use data throughout all workflow of your whole organization. And they use the transformation of climate data into bespoke knowledge services. So again, climate services are very different from, for example, weather services, which are used by anyone with the same visualization, but they require the user to be included in the process in order to be effective. Now, the method that we're using by using business models as a lens put true transdisciplinary at work. So the first step is to create the business model by sketching the business model. The second is to organize business model, collecting barriers and opportunities, understanding what is the taxonomy behind the set of business model existing. The first step and the fourth are connecting. They are image and forecast. So since business model are an evolving logic, we need to imagine the climate services going throughout time, in the medium up to 5 years, and in the long run more than 5 years. And we need to do it qualitatively through some tools that are coming from sociology and business literature, and quantitatively through, for example, metrics that are normally embedded in the business plan. The 5 and 6 steps are also connected. They are called know and position. This is, by the way, an original framework that we developed that is currently under review in a paper. Knowing means knowing your customer. This is not enough. It's not enough to talk about co-creation by, for example, using interviews or surveys. We need to complement all these tools by truly engage with the so-called user that becomes a client and the customers and need to satisfy it, but to also cooperate in order to generate this co-created knowledge. And understanding where we are, so our positioning in our target market, allows to avoid deficiencies. So allows to learn from competitors, learn from best practices, and understanding and forecast the future shocks. So the sketch uses some of the most famous tools. For example, on the left-hand side is the business model canvas, which is not the business model, by the way. It's often confused, but it's just a tool. It's a visual tool that describes a given business, in this case, a climate services, by 9 building blocks. That describe how the value is created, how the value is generated, how the value is retained and ultimately delivered. There are different tools available. This is the business model canvas, but one other example that we used in another project, Safer Places, is the lean canvas. The value proposition tool is another example. And finally, in the climate services realm, we understood that these tools maybe not as appropriate as we thought. So we simplified this tool and we modified it in order to express and explicitize really what is the value proposition and how the network is actually generated.
Francesca,
if you remember,
2 minutes. 2 minutes.
Yes, if you remember, climate services are again KIPs, therefore they're very dependent on the network. The point is to organize by connecting barriers. We organize the barriers in order to generate free patterns, so free business model patterns that describe a given way of generating and creating value. And then there is the image and forecast, as I said, where we're using qualitative and quantitative tools in order to describe the business model. The final set is to know the ideal customer. As I said, you need to use surveys and interviews, but also workshop in order to engage with the user that you detected in your reference market. And position is giving you precisely the evolution of the market that you target. So by comparing you and your competitors in the reference environment. So practical examples of CLARA business model are usage-based and software as a service. So customers on one hand side are paying an amount to the company based on the level of usage, while on the second case, a servicing company sells a subscription-based licenses for cloud-hosted software solution. We understood the importance of engagement in the case of climate services through the multi-user forum, which is basically a set of stakeholders coming together to discuss different tools available. And we finally decided to create a method that can be replicated by anyone, which is a game that is available at the end of September, which collects all the tools that I've just described in this presentation and will be available and downloadable at claraproject.eu. If you do have any question, please reach out, and thank you for your attention.
Thank you very much, Francesca. I'm just checking. If you have a question to Francesca, please step forward. If not, I would ask you, Francesca, the same question. You know, in the coming years, in terms of business model innovation or business model thinking, where do you see the major breakthroughs that we can expect?
I think that technology is really shaping business model innovation. So we need to make use of new technologies and new forms of data in order really to support innovation, but also we need to include more actors in the way we create and generate value. So this means financial operators, yes, insurers, yes, but also the civil society, because business model, again, describe the set of strategic choices, and strategic choices must include everyone in this process.
Thank you very much. And this wraps up the first half of our breakout session on adaptation modeling and sectoral adaptation. We will have now the coffee break, and we'll get back in 22 minutes and 11:30. The same link, so you might not disconnect, but stay connected if you want to follow us, you know, for the next hour, starting from 10:30. Please feel free to connect earlier, to get back earlier, just to perhaps exchange some ideas with the other speakers and talk about the papers. So, but the streaming will start at 11:30 with our next speaker and our new moderator that will be at Jochen, who will replace me. So in the meantime, just, you know, enjoy the coffee break and look forward to seeing you in 20 minutes. Thank you very much.
So welcome back, everyone, to the community workshop. Again, we have 4 excellent speakers that will be giving their presentations on different topics related to modeling and climate change adaptation. The first speaker I want to announce is Virginia Murray of Public Health England, and she will be giving a presentation on health challenges and opportunities. Please, Virginia, the floor is yours.
Thank you so much for introducing me, and it's such a privilege to be part of this climate adaptation modelling community workshop. To me, it is a really vital piece of work that you're doing, even if we're doing it remotely, but it does keep our carbon footprint down. This is a piece of work that I've had the privilege to do with Tim Chadbourne, who's our head of behavioural insights and our evaluation lead, but also who's a member of the World Health Organization Technical Advisory Group on Behavioural Insights and Science for Health. And we know that societal transformation is a difficult topic for many people to follow and see how we can influence. So I'm going to talk a little bit about what social transformation is and how societal transformation works in action with COVID-19, touch the climate change driver from the health aspects, give examples of intervention methods, but also take you to some conclusions and recommendations and my lovely network with the Wellcome Institute, who've been able to very kindly share with me some ideas on planetary health at the end. A bit of fun in a world that is so difficult. UNESCO have been doing a lot of thinking about social transformation. They've come up with a definition which I particularly like. The world is undergoing important social transformations driven by the impact of globalization and global environmental change, economic and financial crises. It results in growing inequalities, extreme poverty, exclusion, and the denial of basic human rights. These transformations demonstrate the urge for innovative solutions and trying to bring values of peace, human dignity, gender equality, non-violence, and non-discrimination. But most importantly is to bring young women and men who are the most affected by these changes and are hence the principal key actors of social transformations. And we know that with Greta Thunberg, a lot of the drivers have been from the young people who really are telling us that we need to think about this very seriously. So I thought I wanted to give you an idea of societal transformation in action. COVID-19 has been a massive global pandemic. It's a crisis. It's affected large-scale behavior change with societal transformation. These changes is placed on all of us with huge psychosocial burdens on individuals to help human behavior with the recommendations of epidemiologists and public health experts. And finally, we know that it's taught us a lesson of how closely environmental, societal, and human health are connected. So if we turn to the climate change driver, the Lancet Countdown very clearly reports the effect on every child born today will be profoundly impacted by climate change. This is going to change the extremes of weather, the water and food security, changing patterns of infectious disease, and basically a less certain future. And without accelerated intervention, this new era will define the health of people at every stage of their future lives. So this global crisis in climate is an existential threat as we know it. And without a radical abatement of greenhouse gases, global warming will reach and exceed 3 to 4 degrees before the end of the century. And that will have a really detrimental effect, which is summarized today only in seeing the impact on the Antarctic glaciers. So there are many things that we need to look at directly and indirectly that the Lancet reported on last year, and we know that we need to keep this in mind about how we manage for the future. So let's just think about some strategies to invest in for the adaptation to climate change with societal transformation. Enhancing early warning for extreme weather events and their cascading and complex hazards and risks are critical. We know some humans are much more vulnerable to some of these effects, but also some people don't believe in these effects and so may not get out of their way. We know that we need to emphasize the value of active travel and public transport, something that the Intergovernmental Panel on Climate Change has been really focusing on in the AR5 and AR6s. We need to reduce outdoor coal power station outputs, but also household air pollution. So wood-burning stoves are increasingly becoming a concern for all of us. And in Europe, these are very popular at the moment. We need to encourage sustainable and healthy diets, reducing the amount of meat consumption. We need to reduce the use of fossil fuels and plastics, particularly as we hear more and more about plastics in the ocean and the impact of that. And ultimately, we need to build sustainable and healthy cities. Now we have techniques, inside health, which are known as interventions of choices. And the Nuffield one is a really useful one. It has a ladder, the principles. What can you do most that will most change, but maybe a very forceful change, to what can you do just by watching? So you can eliminate choice by legislating to stop highly polluting vehicles entering urban areas. Or you can restrict choice by regulating standards for approved wood-burning smokeless zones. We can guide choice. We can encourage by fiscal measures to increase the cost of fuel to shift towards electric vehicles, which we think is very important. Or you could guide choices by incentives, offer a tax break for purchasing bicycles to travel to work. A really good idea. Or we could guide choices by changing the default policy, by encouraging restaurants to provide vegetarian-only cuisines. Or we might enable choices to enable individuals to change their behaviours by using cycle lanes. So we have a lot of cycle lanes going down in London at the moment. Or we could provide information, so in campaigns to encourage the the use of plastic carrier bags, and we are about to come back into that very strongly, making them much more expensive. But is that just guiding, or is it actually delivering at a higher level on the ladder? And finally, the one option we don't have time for: do nothing, or simply monitor the current situation. We know we should not be doing that. Now, in our world in health, we know that there are some things that work really well. So we have something that's known as the behavioral change wheel. This wheel where you look at all the options, be it on what you could do in these fiscal measures, to environmental planning, to legislation, to how you can enable people to get involved by providing restrictions, education, perspectives, possibly training, even coercion. But then you have at the heart of it something that we really like: the capability, the opportunity, the motivation to change people's behavior. So developing behavioral change interventions from scratch can be done this way, or we can build on or modify existing interventions, or we can choose from existing or planned interventions, all of which could have an impact upon climate change, which we think is really important. So let's have a little think about these options. Well, you can do things by assessment. You can evaluate the appropriateness of existing or proposed interventions. We have criteria known as APs, which look at acceptability, practicality, effectiveness, affordability, side effects, and equity. So we're building a life cycle of knowledge to try and get people to understand what might be possible. We can go for the behavioural selection, as I've suggested before, identifying and selecting key behaviours to focus on to achieve policy objectives. Or we could turn to capability, opportunity, or motivation, the combi diagnosis, where we can get the desired behavior because there's a target group which sees the capability, opportunity, and motivation to engage in such behavior. So we know that in London we're trying really hard to encourage people to use their bicycles so they don't go on public transport, reduce the risk of being exposed to COVID. Or we can select intervention types. Maybe we can do this by using broad types of intervention, looking again at these combi diagnostics of education, persuasion, incentivization, coercion, training, environmental restructuring, modeling, and enabling. So this is taking modeling slightly differently out of the classic modeling that so many people in climate change think about. It's not just where it's going to be hot, it's trying to understand how we can change behaviors to interpret where it will be hot. And then formulating an implementation strategy, choosing how to deliver this as I started with. Is it going to be legislation, service provision, fiscal measures, guidelines, environmental or social planning, or communications and marketing, or even regulation? And then constructing that intervention, deciding the details of the intervention content and delivery in partnership with people who might be able to use this. So in conclusion, though we feel that COVID-19 has really shown pandemic representation and offers a massive global opportunity for behavioural change with societal transformation, it has been an opportunity by which we can look at processes whereby control measures of effective hand and systems of effective hand and respiratory hygiene, social distancing, self-isolation, which have helped to implement across citizens across the world to try and reduce some of the impacts of the COVID-19 pandemic. And by using a systems approach, we think we can determine and deploy a cost-effective mix of policy options according to the intervention ladder and the behaviour change wheel, which might assist in delivering societal transformation actions. This is ambitious, but we really have to remember that it is the young women and men who will help us to take this through to really introduce innovation activities. And we hope that part of that will be driven by the launch of the EC research funded innovation programs that will be launched in 2011 to mobilize investment in EC-wide effort in immeasurable and time-bound goals around issues that affect citizens' daily lives. And Jaroslav, you have been so involved in trying to take this forward, and I've been privileged to sit on the mission to try and see how we can get that engagement and bring all these good public health measures that we know so much about to the fore and trying to get that to be delivered. Now, we know that planetary health is where we're going. We need a world that ensures that that Earth is a healthy home for humanity, for all, for everyone. To do this, we must have sustainable, healthy cities with more urban green spaces, with places where people can cool down, or there are opportunities to manage floods more safely. We know we need to develop sustainable and healthy diets. Only by doing that can we reduce some of the greenhouse gas emissions. We know we need to engage with active transport to reduce air pollution and carbon dioxide emissions and reduce deaths and injuries from car crashes as well as asthma and other things. But we also know that we must stop using fossil fuels and move to clean, renewable energy. And that is a very big drive in the United Kingdom, but also across many countries in Europe. And this will really save lives too. And if we do this, why does it matter? We will reduce the accelerated environmental changes which pose such a big impact to health. We will engage everyone and unite people so that it won't affect us all, and we'll have a future that will engage much more positively than we fear at the moment if we look at the potential for a 3 to 4 degrees. Thank you for the opportunity to share these messages and ideas, and your comments would be so welcome.
Well, thank you very much, Virginia, for this beautiful talk you gave with a lot of valuable lessons, I would say, and also by pointing us to, well, a rather different category of tools that we have been talking about so far, especially on influencing and getting behavioral change done. I'm looking at the audience now if there are any questions, so please speak up or raise your hand if you have any questions for Virginia. I don't see or hear any. It's well, it's a different way of having workshops than we're used to, obviously. I have a question to you, Virginia, as you're was also referring to the EU missions and the research and innovation agendas for your particular line of work and getting these behavioral changes really happening. What sort of research and innovation projects would you recommend for the coming 5 years, so to speak? Can you give some details or maybe some examples of what you think are good projects that the Commission should stimulate in the near future?
Well, we're really concerned that so many people do not understand that it's really going to be behavioural change of individuals that will make the greatest difference. What we have seen is people are beginning to discuss it. We have various action groups who are trying to push this, but we also know the Intergovernmental Panel on Climate Change have been really concerned, particularly from the health aspects, to try and change our behaviour. So I'm trying to take you into the future to look at the systems that we have developed from the health aspects about how we can change people's how they live. I'm sure you have a bicycle, I have a bicycle. I'm sure you use public transport, I have public transport. I'm sure you will probably mostly eat vegetarian food, so do I. We try and change our behaviour. We try and change it so that we reduce the impact for the future. We try and make sure our homes are much more sustainable, that they don't lose heat, that we don't waste energy, that we try really hard to engage in a way to deliver much more clearly how we should achieve the future. And it's only by building that partnership can the classic climate modelling impacts actually change how we deliver this. And that's why this mission that the European Commission has included as one of its moonshots on climate change adaptation with societal transformation being such a key process. And I'm very glad to say health and well-being has a very strong vocal point in vocal messages in the proposals for those projects.
Thank you very much. Yeah, for the sake of time, we have to move on. I see in the meantime that there were some remarks and questions in the chat to your talk, so maybe you can respond to that in the chat. I have to move on to the next speaker, which is Kurt Christian Kersebaum, who will give a presentation on modeling to evaluate climate resilience of crop rotations under climate change. So please, Kurt, can you change your screen with us?
Do you see my screen?
Yes, yes, we do. Thank you.
Okay.
Please go ahead.
Yeah, thank you very much for the invitation and to give me the opportunity to talk about modeling of crop rotations. So we switch now to the area of agriculture, which is an area which is very much exposed to climate change. And why is this focus on crop rotations? Usually diversification of crops in cropping system is suggested as one option to increase resilience of crop production under climate change, mainly to reduce the risk of which is posed to a specific crop, and that farmers can avoid total failures of their crop production, just sharing the risk, having different crops on their fields. Nevertheless, most model-based studies so far are focused on single crops and use multiple year simulations, but with annual reinitialization. However, there are good reasons to look at crop sequences over a longer period, since crop rotations and residue management, tillage, fertilization, and water management have some effects on soil carbon storage, water and nitrogen dynamics, crop yields, as well on the short as also on the long term. Additionally, arable use of soils is often linked to problems with nitrogen emissions, soil degradations, for example, loss in soil organic matter. And therefore, the design of cropping systems has to consider more than crop yields to achieve a sustainable crop production. However, this adaptation needs to be site-specific because there are different responses. And moreover, the best management practices of today might not be the best under future climate conditions. Therefore, the modeling of soil-crop atmosphere interactions can be used to assess the multi-criteria performance of crop rotation designs and management. So in the following slides, I will give you a few examples how modeling can be used to assess the performance of crop rotations, considering several aspects beyond crop yield. To start with a more positive example, because depending on environmental conditions, climate change might not only be a challenge, but may also provide new opportunities for crop production. So, for example, global warming will prolong the length of the possible growing season, especially in the northern latitudes, and allows the growth of crops which are so far too much demanding regarding their temperature requirements. So modeling offers the opportunity to model crop rotations, new crops, and cropping systems for adaptation and testing these opportunities under climate change conditions. In this example, we try to introduce a double cropping system in Germany, which was so far rarely practiced because the growing season was too short. And we also used experimental data to parameterize new so-called exotic crops like sorghum or Sudan grass. And we have tested these different crops as sole crop or in combination in a double cropping system with winter rye as a winter crop and then the sorghum or the Sudan grass as a second crop. What we see is that in general, the double cropping system outperforms the biomass production of the solid crop, although the second main crop biomass is reduced. but especially under the climate change conditions that you see here in the lower left figure, the winter rye clearly benefits from warming. So the number of growing days increased by about 50%. So the total biomass of the double crop system outperforms the sole crop system even under future conditions. However, we see that there is an increasing competition about water resources. On the right side, you see in the upper part the soil crop system, where you see that we have an increasing summer drought under climate change scenarios towards the end of the century. And in the lower part, you see the double cropping system, where you see that the second crop or the first crop leads sometimes that the water holding capacity is not really filled up as usual in winter. And so the second crop will increasingly suffer from water shortage. Another problem related to arable cropping systems is water protection. We often see that arable crop systems have high losses of nitrogen and pollute groundwater resources and surface water resources. And it is well known that some introduction of cover crops over winter can reduce this nitrogen flow and pollution of water resources. Here we have an effect where we have the rare occasion that we can measure this effect by sampling tile drains. And you see on the right, on the left side, in the upper part, the water flux, the percolation without cover crop, and on the right side with cover crop. And on the bottom part, the nitrogen losses. And the modeling in this case really reflects well the nitrogen losses, but it slightly overestimates the water consumption of the cover crop. The reason here might be that parameterization of water demand of cover crops is not very well established, but there is another aspect which is shown in this long-term simulation. Of course, in the beginning, when you have the termination of your cover crop, you start with a lower water content due to the water consumption of the crop. But because you are mulching the crop residues, the soil is prevented from unproductive soil evaporation, which is seen here in the lower part for the following corn and the following soybean, that the evaporation from soil is lower with the cover crop and mulching as without cover crop. So the mulching can overcompensate the higher water use of the cover crop. When we simulate the effects of different crop rotations over a longer period, this is preliminary results from a regional study in Brandenburg, which was one of the driest region in Germany. We see high differences between the different crop rotations and also among different site conditions. There is an increasing soil quality from the yellow one, which reflects the poor soils, to the green ones, which reflect better soils with higher water holding capacity. So we have higher emissions on the poor soils and a strong effect of the different crop rotations. We also have effects of irrigation, which might increase the nitrogen use efficiency in the crop rotations. And we see also an effect of climate change here, which usually increases nitrogen leaching because nitrogen use efficiency under summer drought is decreasing. However, models are quite capable to reflect these relations of soil, water, and nutrient transfer. in crop rotations, but there are some points which can be observed that, for example, the pre-crop has also an influence, even if you compensate the different nutrient starting points. Here, an example of wheat-wheat combination in comparison to oilseed rape wheat and oilseed rape wheat combination. And it seems that there are reasons beyond water carryover which are beyond the water and nutrient carryover. This effect is higher if you have water deficiency in spring. So far, there are very few models here. I show one example which was recently published in Soil and Tillage Research, the Simplace model, which considers also the effect on the root distribution of spring wheat after different previous crops. Another aspect which is so far not well described is the impact of pests and diseases. There are 4 components which are defined for a disease framework by CREA in Italy. The first one is to describe the inoculum pressure. This is a topic which is quite strongly related to the crop rotation, which might influence the survival of diseases or pests. Then the disease progress, that's a part which is mostly covered by disease models. But then the linkage of the disease to the impact on the crop is to estimate the crop losses which are related to these diseases. So far, we can consider 7 generic damage mechanisms can be implemented into different crop models, but the implementations, as you see in the lower part, has some very high variability due to the variability in the model structure. Although we use the identical injury profiles and damage mechanisms.
Can you
finally, the agro-management.
Yeah, sorry.
Yeah.
Can you come to a conclusion, Kurt? There's time left. Yeah.
Just another thing of long-term effects that crop rotations have an influence on the carbon sequestration, but this increasing carbon sequestration reaches a plateau, and this might be contradicted by climate change as well. And finally, we have to consider that carbon sequestration might be linked also to higher emissions, for example, for N2O emissions, which needs to be considered in modeling. Coming to this summary, the response to water and nitrogen is usually well considered by models. However, the effect of the crop rotation regarding carryover effects are often not addressed in climate change studies. The effect on crop yields is often masked by a high level of fertilization, but when we go to cropping systems which are under limitations, the effect is much clearer, and we have to consider these long-term experiments on soil properties and their feedback to crop production. I finally had a few points for crop model improvement. That is related to the data which are necessary to parameterize crops, for example, functional crops like cover crops, to have a better selection of suitable crops under specific conditions. Effects of extreme events need to be better considered. We have to better capture these extreme events with crop models. But so far, mostly field trials are cancelled when we have a disaster event, and this needs to be better documented instead of cancelling experiments.
Okay.
Finally, effects of tillage are not well represented, and we also need to work on the link between pest and disease models and crop models. Thank you for your attention.
Thank you very much, Kurt, for this comprehensive overview of crop modeling, and also the plea for better looking at crop rotations and look at multiple benefits and criteria and evaluation. Unfortunately, there's no time to take any questions publicly. I've seen there is a question in the chat to you, so maybe you can chat in the chat and try to follow up the discussion there. We really have to go to the next speaker. So thanks again, Kurt. And the next speaker is Dionisio Perez Blanco, and he will be talking about how to navigate deep uncertainties in human water systems. Dionisio, can you share the screen with us?
Hello, everyone, and thank you, Jaro, for the invitation, for the possibility of being here today and make this presentation. It was very interesting to join the workshop and this session thus far. I decided to change the title because after Edoardo's and Hans presentations, and also Virginia's presentation as well, I realized that they were underlining the importance of integrating socioeconomic behavior into this physical modeling that they were presenting, and this is precisely what my presentation is focusing on. The objective is more of a conceptual presentation. Tomorrow I will present the model that underpins all these, that applies all these concepts. But today I wanted to discuss how we can start introducing a comprehensive way human systems into the modeling of hydroeconomic systems, so to account for deep uncertainty. And this is a challenge that we have had for many years now, and we have started to address, but still there are many challenges pending. Okay, I'm going very quickly through the first slides because I think that after Edoardo's presentation and the others, this is well, probably this was already familiar to most of you, but in any case, we have already dealt with that during the first presentations. So what's deep uncertainty? Well, deep uncertainty is a situation in which we are not aware of all possible futures. This is called deep uncertainty type 2, which is the deep uncertainty we try to deal with modeling when we use these ensemble experiments using multiple models, perturbed physics ensembles, or multiple scenarios. We are generally trying to deal with this deep uncertainty type 2. But there is also a deep uncertainty type 1, which happens where you basically don't know what possible futures lie ahead of you. So under deep uncertainty, what we know is that conventional decision making, which is based on optimization of a set of futures which are probability associated, doesn't work anymore because basically we don't know what's the probability of each future. But moreover, there are some futures that we may not be capable of predicting, of anticipating. And a good example of that is the COVID-19 situation that we are living right now. Hans, in his presentation, already mentioned that, well, in the predictions that they made, they were not able of anticipating this, as happened to all of us. And that's a situation in which we are facing this sort of deep uncertainty type 2. I'm going to start my presentation by dealing with the relatively more easy part, which is deep uncertainty type 1. As I mentioned, there are 3 sources of deep uncertainty type 1. Well, you may have problems with the scenarios. If you make too much assumptions about these scenarios, you may run against a scenario that you didn't anticipate it, and then your predictions fail. So you need to sample a scenario uncertainty. You also need to sample the uncertainty related to the parameters and also related to the structural uncertainties of the models. This is something that has been already done. A good example is the IPCC. The IPCC takes account of all these 3 sources of uncertainty. Also, hydrological modeling ensembles such as APEX take into account these sources of uncertainty. What these sort of modeling exercises do not take into account is the uncertainty that may arise from the fact that we live in coupled and complex human water systems or socio-ecological systems, in which it's important to understand what's uncertainty related to the physical system, but also very important to understand what's the uncertainty related to the human system. And Virginia was talking about the importance of changing behavior. I agree with that, but obviously what happens when you change behavior is that you're changing also the human responses and therefore the impacts on the physical system. So basically everything changes. So once you are taking into account human systems, you need to model somehow what's the interactions that you have between the human and the, in this case, the water system, but also any other ecological system. And that requires an in-depth understanding of the interlinkages between the two. So what I'm trying to address very quickly today in the first part of the presentation is what can be done to deal with this type of deep uncertainty type 1 with human systems. Thus far, what we have done to model human systems is, at least in conventional hydroeconomic modeling, is to rely on integrated assessment models. What we used to call holistic hydroeconomic models. These holistic hydroeconomic models basically simplify very much the human components. So they put most of the effort in representing the physical system, and then the human system is represented in a very simple way. The problem with that, obviously, is that, well, while you can get very high-end simulations, very precise simulations, well, a model that is accurately predicting what happened in the past with a very low error, the understanding may be a little bit less good because you really don't know why farmers are reacting, or why agents, in the case of water use, we may think of farmers, are reacting that way, because you are not fully modeling them. You are using piecewise equations that relate a response to a shock, and that's it. You don't know the dynamics before that. So what we propose to, what I will propose here, and this is a collective research, collaborative research I've been conducting for many years with colleagues from CMCC, is to work using a protocol-based system in which you basically model all the different systems that are relevant to understand the problem at hand individually in modules, and then you connect them through protocols. And this is what you have here. So basically what we have here is a representation of the human system in which we have two different modules, the microeconomic module that represents the behavior of the agent, and the macroeconomic module that represents the behavior of the macroeconomy, i.e. the interactions between different sectors and through trade, for example, and also between different regional agents, such as countries. And then we relate all that to the water system. I'm going to show tomorrow an example of how this works in practice. But basically, the concept that I'm trying to present here is that, well, the raison d'etre for this modeling is that if you want to represent human systems, you need to be aware of the intrinsic complexity of the system. These systems are not easy to model. So if you want to model the human and the water system in an integrated model, probably you're going to run into problems because the optimization functions, they are very different. And you may have some complex to integrate them in an integrated assessment model. And probably what you have to do is to sacrifice the complexity of one of the two systems in order to have a common, a single solution. So one approach is to use this protocol-based modular approach, in which basically each different system is represented individually in a module. Each module represents a full-fledged microeconomic, macroeconomic, or hydrologic model. And then you try to connect the different systems through protocols and look for convergence through iterations. That's what we are. That's the approach that we are adopting here. This way, it's possible to model the cascading uncertainties that you have between the human and water systems. Obviously, there are some computational challenges because this is computationally expensive, but we have been running these simulations already. Well, they take a few days to be run, so it's not a rapid assessment precisely, but it works, and then you can get some results. Comprehensive assessment of uncertainty, you sample uncertainty, and then you can feed this information to policymakers so that they are aware of the uncertainty that is related to their decision. Now I'm going to deal quickly with the second problem, deep uncertainty type 2, and I'm trying to present how social sciences can contribute as well to deep uncertainty type 2. So, well, an obvious question that we can make here is what can be done when the only thing we know is that we don't know? Because the problem with deep uncertainty is that we know that we don't know what will happen in the future. So what can be done? Well, there is one thing that can be done, and this is an area of research that has been advanced very recently by, well, lately, not very recently, in the last decade, let's say, by institutional economics, which is strengthening the adaptive robustness. Basically, strengthened adaptive robustness means that you are going to increase the capacity of institutions to adapt to new shocks. How can you measure that? Well, it's possible to measure that. I mean, indeed, economists have been measuring this. We have been measuring this for many years. Jaro and I had a student whose PhD was basically focusing on that, and we have some quantitative estimations on the adaptive capacity of an institution, in this case, the Po River Basin Authority, and its adaptive capacity to droughts. So basically what we need to devise now is a tool to predict from past effect, from the past performance in terms of adaptive robustness of institutions, the future performance. This is the challenge. So we already know, we already have tools to measure whether an institution has been adaptively robust in the past. Please. Ah, okay. So basically the challenge now is to measure that in the future. So basically, very quickly, this is the framework that is proposed by Garrick to do that. So basically, in order to know whether an institution is being adaptively robust, we need to know how well the objectives have been met. We need to have information on the total program budgets, and then we need to have information on the public transaction costs. And this is the real challenge, because while we have information on the two first points, we don't have many longitudinal assessments on public transaction costs. The information that we have thus far is very reduced. And in Europe, at least in terms of water institutions, I'm aware only of two studies, of two data sets on public transaction costs. So once we have public transaction costs, we need to check whether they are being reduced along time. And this is what we can do. Well, this can be easily done using a time series analysis. This is an example for the Murray-Darling Basin in Australia, one of the few places where we have longitudinal assessments for transaction costs for a reasonably long period of time, since the 1980s. And here what they are trying to show is whether these transaction costs are being reduced or they are being increased. If they are being reduced, then we have an institution that is being adaptively robust. If they are not being reduced, if they are showing a constant trend or they are increasing, then we are not performing well in terms of adaptive robustness, which will mean that in case of having a future shock, the institution will struggle to adapt, because past performance is indicating us that it struggled to adapt in the past. So in the future, it will probably do as well. So to conclude, well, under deep uncertainty, the final decision follows heuristics. So the tools that I've been showing thus far, either if you are dealing with deep uncertainty type 1 or with type 2, what you're going to handle the decision maker is a big set of simulations in the first case, and in the second case, a trend of on what institutions have been doing in the past. Then how decision makers weight each one of the two products is completely based on their preferences. So we can anticipate what they're going to do. So in the end, we are just trying to, what we can do here is to facilitate the best information and the most comprehensive uncertainty sampling to decision makers, so that they in the end can decide what to do, building on heuristics, which in the end is one of the most important things and one of the least explored things in terms of managing water resource management. So well, thank you for your time. I think I'm done, and if I have time for questions, I will be most happy to reply them.
Well, thank you, Dionisio. Unfortunately, we are running out of time a little bit. I think you have been presenting very important work. And just one question that I'm also curious in is this is great work with mainly done by academic institutions at the moment. So my question would be, what will be needed in the coming 5 years to have these modeling techniques being incorporated in more regular adaptation tools and software and climate services?
Okay, yeah. That's a very good question. That's a very good question. Well, regarding the first part, the modeling, let's say the most conventional modeling part, where I presented the protocol-based modular approach. Well, I guess we are very close to deliver this to the market, let's say. So we have institutions which are already using this tool. The protocol-based modular approach. Here in Spain, the Douro River Basin is conducting the cycle of river basin planning using this tool for the socioeconomic assessment. So it's already being used, but it's not a rapid assessment. That's for that we will need to make a better integration in the future. For the second part, we need data. We don't have data. That's the problem. It's mostly a conceptual idea that we have tested here in Europe for the first time a couple of years ago. It has been tested in Australia and in the US, but databases are very, very limited, and the data that we have is not. We don't have longitudinal data sets that allow for the comparison of transaction costs throughout time. So I guess that's what we need to measure transaction costs from the beginning, and that will pay off in the future, of course. But right now, we don't have many transaction cost data sets.
Thank you, Dionisio. We need to move on. There is one question in the chat as well, so maybe you can have a look.
Yeah, sure.
There. So the last speaker is Manuel Pulido Velasquez, and he will present on a top-down means bottom-up approach for climate change adaptation and water resources system. So Manuel, the floor is yours, and please share your screen with us.
Thank you. Thank you for the presentation. Can you see my screen now?
I see yourself, not a presentation yet.
Okay, sorry. Let me check.
Yeah, it's coming.
Now it works.
Yeah, there it is. Yeah. Okay, maybe you can switch to presentation mode.
Yes.
Yes.
Okay, now?
Yes.
Okay,
great.
thank you.
Please go ahead.
Okay, so I'm going to talk about the top-down meets bottom-up approach for climate change adaptation in water resource systems. First, I would like to mention that I'm the director of the Research Institute of Water and Environmental Engineering at the Technical University of Valencia in Spain, leading academic research center devoted to the interdisciplinary study of water challenges. So the projected changes in temperature and precipitation in Europe indicate that the differences already existing between the wet regions in the north and the dry regions in the south of Europe are going to increase. These changes in precipitation and temperature will have an impact on the hydrological regime, and all the existing climatic and hydrological evidence and projections indicate that water resources will be seriously affected by climate change. If in the case of the Mediterranean regions, the projections are quite consistent. We are going to see a decline in available water resources and an increase and intensification of extreme events, drought and floods. And this is going to clearly lead to an increase in water management problems with significant environmental, social, and economic impacts. Moreover, the real challenge is not only to adapt to climate change, but to cope with climate change, including other key significant drivers of change, such as population growth and concentration in urban areas, socioeconomic development, and the need of efficient and sustainable water, energy, food, and ecosystems nexus. So the challenge of adaptation in water resources system includes coping with high and deep uncertainty on future resources and uses. Also, the need to deal with multiple objectives and multiple decision makers, which is innate to water problems, which has been often classified as weak management problems. And also that there is a broad range of feasible adaptation options that can be implemented, from a structural solution to non-structural measures, including regulatory and economic instruments. But in any case, uncertainty cannot be an excuse for inaction. So we need to set flexible and dynamic adaptation plans that have to be economically efficient, socially acceptable, environmentally sustainable, and have to be robust to climate change and other future uncertainties. These are key requirements for the success of any adaptation strategy. And however, the integration of these different factors in the adaptation planning process is a complex issue still to be solved. So I'm going to present a framework to include these attributes in the development and the selection of adaptation portfolios for river basins or water resources systems. But then we have the problem that when defining an adaptation strategy, going from global and regional projection to the study of local impacts in order to define adaptation responses, using the classical top-down approach, we face what have been called the cascade of uncertainties, which uncertainty expanding at each of the steps. So the approach we propose is a framework in which we have a top-down approach first for the assessment of climate change impact at a local scale, and at the same time we use a bottom-up approach for the definition of future land use scenarios and catalog of local adaptation measures in a way that we call top-down meets bottom-up. So the top-down approach relies on a chain of models to assess the local impact of global change, starting from global and regional projections, and using a range of different climate projections. But on the other hand, the bottom-up approach is going to determine future demand scenarios and locally prioritized measures, or adaptation measures, identified through a combination of a participatory approach with a relevant expert and models used to characterize land use and water demand changes. In order to develop future land use scenarios, particularly for agriculture, we may use two different approaches. Either we model land use change using artificial intelligence techniques that are able to learn from past changes, or we can also use participatory approaches with the relevant actors through scenario building workshops. Participatory approaches can be used for a scenario building in order to develop alternative futures or plausible simplified description of how the future might evolve. We can have more qualitative or more quantitative approaches. In our case, we use qualitative narratives, so we use storylines and we translate them into quantitative scenarios that are used as input of models in order to assess the impact of the projected changes. So we have applied this approach, for example, in the Júcar River Basin, in the two main agricultural areas, the Mancha Oriental in the upper basin and Ribera del Júcar in the lower basin, for which we use the shared socioeconomic pathways, which represent different pathways to future societies and that are linked to the emission scenarios, to the representative concentration pathways. And the global scenarios were translated into local narrative after consultation with the experts. And then we translate them into fake future press news that we use as a starting point to be presented to the farmers in the workshops to discuss local future scenarios. So we conducted two first scenarios related to agriculture in the two main agricultural areas to discuss future scenarios for agriculture and potential adaptation measures. And we use this information for a third workshop to discuss solutions for climate change adaptation at the basin scale. So we discussed advantages, problems, obstacles, and prioritized the measures. And we also discussed how to deal with the management of the basin, including projections, more extreme scenarios that were projecting a reduction of the mean annual inflow to the basin up to 40%. Then the two approaches, the top-down and the bottom-up approaches, converge in our method, converge into an integrated water resources management model for the selection of least cost portfolio of adaptation. And given the uncertainty of the global chain scenarios, we have to, the resulting adaptation portfolios are climate check across the different projections in order to define a robust, least regret program of measures for adaptation. We have applied this approach to two cases, one in France in the Haut River Basin, Mediterranean basin with expectation of high population growth and quick expansion of irrigated vineyard, and also in a larger basin in Spain, the Júcar River Basin, with a high share of water used for irrigation and long recurrent multi-annual droughts. I'm going to focus, sorry?
2 minutes, please.
Okay, I'm going to focus on the result for the first case. So we estimated the local impact of climate change on water resources, and we estimated future scenarios of demand and adaptation measures for agriculture and for urban demands, combining participatory approaches and water demand models, and all these were input for a least cost optimization model to determine a least cost portfolio of measures. As I mentioned before, that was climate check across the different projections to make sure that we have a robust solution given the uncertainty. And finally, we also address the issue of allocation of the cost of the adaptation program. This is a key aspect that is often not considered. And in order to address cost allocation, we compare two different approaches. Cooperative game theory, which is given the solution of cost sharing considering the economic logic, versus well-known social justice principles applied to the definition of cost allocation criteria, and then we tested the acceptability of these using surveys. So finally, with this approach, we were able to integrate, to fit in the different pieces of the puzzle to design, evaluate, and select a portfolio of adaptation measures to climate change that comply with the 4 objectives I mentioned at the beginning. Economically efficient, using the least cost river basin optimization. Environmentally sustainable, using the environmental flow constraints. Acceptability, because we use a bottom-up approach for defining future local scenarios and adaptation responses, and also because we address the issue of equity in cost allocation for adaptation. And finally, climate robustness by checking the portfolio of adaptation across the scenarios and selecting least regret and robust options. And that's it. Thank you very much.
Thank you very much, Manuel. I'm looking if there are any questions raised. I don't think so. Just one question to conclude. I think most groups will be a little bit late for the plenary section. So I think this is fantastic combination indeed of top-down and bottom-up approaches. I was wondering, how do you look at specific vulnerabilities or accepted service levels? Is this also something you determine bottom-up in your approach?
A specific, sorry, I didn't...
Service levels.
Surface?
Service levels of water supply, water allocation.
Yeah, we did. I mean, our analysis was, the purpose was selecting adaptation portfolios at the basin scale of water resources systems, but then considering the local conditions. So our bottom-up approach were based on studying the local responses that were applying in the past, and also organizing workshops with the key stakeholders in order to select future scenarios and catalog of adaptation options. All this was relevant information to feed the integrated water management models that at the same time was integrating the top-down approach. So that was converging into the selection of the adaptation portfolios.
Okay, thank you very much. Well, I would like to continue the discussion because there were so many interesting things presented by all speakers this morning. However, we have a tight schedule and I want to thank you all for participating and invite you to the plenary session where we will share lessons from all parallel sessions that have been going on this morning. And Jaroslav has shared a link of the plenary session in case you don't have it ready at hand. So thanks again, and I hope to see you all in the plenary session. So please leave this session and go to the plenary session.